Now consider the forced response of multi-degree of freedom systems. Let's see how we can deal with that. Let's consider a multi-degree of freedom system. Consider a system with n degrees of freedom. This system can be represented as m times q double dot plus k times q equals, if this system is forced, then I will have a force vector on this side. Now, this equation represents a system of differential equations. They are all coupled. The q vector is basically the vector of generalized coordinates x1, x2, x3, all the way to xn. The matrix M will be n by n, matrix K will be n by n, and the vector F will be n by 1. So now each one of these equations, this is a system of n number of differential equations. Each equation in general will have x1, x2, x3 up to xn coordinates in the same equation. So these equations are coupled, and solving these equations together is not a straightforward process. We've done that for homogeneous or natural response where f was 0. Now f is not 0, it's a forced system, and this system will have two solutions. We will have natural response and forced response, or in the language of mathematicians, we will have homogeneous solution and particular solution. So I have to solve this problem twice. The natural response, we've done that. We're okay with this part, but the forced response is a problem here. The equations are coupled, so what I'm going to do is the following. Now, the eigenvalue problem associated with this system, the eigenvalue problem is k minus lambda m times x equals 0. K and m are the system matrices, and lambda is omega squared. Now this system will have n number of lambdas, will have the eigenvalues. Eigenvalues will be lambda 1, lambda 2, lambda 3, all the way to lambda n, and we'll have also n number of eigenvectors. P1, P2, P3, all the way to Pn. Okay. Now, let's recall that eigenvectors are orthogonal with respect to the system matrices. I'm going to take advantage of this property and try to simplify the system. First, I will define a transformation, the following transformation. First, I will define matrix P. P equals a matrix P1, P2, all the way to Pn. This is the matrix of eigenvectors. Okay, now what I'm gonna do here, I'm gonna define a new set of coordinates. Here, the x's, we call these the generalized coordinates. Okay, and now I will define a new set, and I'm gonna call it lambda. Actually, let's call it eta, so that Q equals the matrix P times eta. Eta, this will be called the modal coordinates, and we'll see why that is. So now I have this transformation. I have my generalized coordinates. I have my matrix of eigenvectors, which I can determine from the eigenvalue problem associated with the system, and I will define this transformation. Now, let me take this and substitute into the equation of motion. Substitute P times eta for Q. So the system becomes matrix M, and instead of Q double dot, I will have P eta double dot plus K, and replace Q by P eta equals the force vector F. Now, I will pre-multiply this equation by P transpose, the transpose of the matrix of eigenvectors. So I will have P transpose times M P eta double dot plus K P eta equals P transpose F. If you expand now, P transpose M P eta double dot plus P transpose K P eta equals P transpose F. What do we have here? Recall that the eigenvectors are orthogonal with respect to the system matrices. P transpose MP, this will be a diagonal matrix. This matrix will be diagonal. And also, P transpose K will also be diagonal. So let me call this P transpose MP, we call it M tilde eta double dot plus K, we call it tilde eta equals, and P transpose times F, matrix times vector is a vector. I'm going to call this new vector F tilde. Now, the M tilde, K tilde matrices are both diagonal. So they are like M tilde 1, 1, 0, 0, 0, and 0 all the way to 0. And on the diagonal, I will have M 2, 2 tilde all the way to M, N, N tilde times eta 1 double dot all the way to eta n double dot plus matrix K tilde is also diagonal, so that will be K 1, 1 tilde and zeros all the way, and zeros, and this will be K 2, 2 tilde all the way to K N N tilde times eta 1 to eta n equals the vector F tilde. Expand this, the first equation, first row, will be M11 times eta 1 double dot and then zeros. So we have M11 tilde eta 1 double dot and then zeros, and here I will have K11 tilde times eta 1 equals F1 tilde. And then the second equation, I will have 0 times eta 1, M22 times eta 2 double dot plus 0 times eta 1, K22 times eta 2, and then 0 multiplies the rest of the etas, so I have K2 2 tilde eta 2 equals the second element in the force vector F tilde. And if you continue all the way to n, the last equation will be M N N tilde times eta n double dot plus K N N tilde eta m equals F N tilde. So what just happened here? I had a system of coupled differential equations mixed in the differential equations. X1 to n are all mixed in the equations, and I ended up with the same number of equations, n number of equations, but these equations are decoupled. Each equation has only one single coordinate. Equation 1 has only eta 1, equation 2 has only eta 2, and all the way down here. So each one of these equations is actually one single degree of freedom system, and they can be solved separately. I can solve equation 1 separately because there's only one variable in equation 1, and I can solve equation 2 because there's only eta 2 in equation 2. So now, instead of solving a coupled system together, n degrees of freedom system coupled, I will solve n single degree of freedom systems separately. And that's why each one of these coordinates, the etas, each one will have a frequency. For example, if you normalize equation 1, divide by M11, you'll get you'll get eta 1 double dot plus K11 tilde divided by M11 tilde eta 1 equals 1 over M11 tilde times F1 tilde. single degree freedom system. So this is going to be omega squared. And this is eta 1, this is omega 1 squared. And you do exactly the same for the second equation. Eta 2 double dot plus K22 tilde divided by M22 tilde. Eta 2 is equal to 1 over M22 tilde F2 tilde. And that's another single degree freedom system with another different frequency, omega 2 squared. So I have now a number of systems, all single degree freedom systems. Each system has distinct frequency, omega 1, omega 2, all the way to omega n. So that's why we call these etas model coordinates, because each one of these coordinates responds at one frequency. Eta 1, the solution of eta 1 will be, eta 1 is going to be some amplitude A1 cosine omega 1 t plus phi 1. One frequency, one mode, only frequency omega 1. There is no omega 2 in eta 1. And eta 2 will be A2 cosine omega 2 t plus phi 2. That's for the homogeneous or natural response. So each one of these variables has one frequency, one mode of vibration. So now I can solve these systems very easily. They are single degree freedom systems. I'll just take my time and solve each one separately and find eta 1 of t, eta 2 of t, eta 3 of t. But I'm trying here to find x1, x2, x3, not eta 1, eta 2, eta 3. The etas do not actually represent physical parameters or physical variables. They're model coordinates, they're just virtual coordinates. I'm interested in the actual motion or in the actual response, x, x, x. So how can I go back from eta to x? Simply use this transformation. Once I have the etas, and I know that Q is P times eta, once I solve for etas using these single degree freedom systems, I will plug my solution here, multiply it by the matrix of eigenvectors. That will give me the response x1, x2, all the way to xn. So now, this way, I converted my coupled, okay, this system is coupled system with mixed variables. I converted it to here decoupled system, which means that all variables are decoupled. Each variable exists in only one equation. Single degree freedom systems can be solved separately for the model coordinates, and then back to this transformation I get to my original generalized coordinates. And this is how we solve and find the response of multi-degree freedom systems, the forced response. First, then I have to solve the natural response problem, which is basically an eigenvalue problem, just like we did in the previous examples. Find the natural response, and then using the eigenvectors and eigenvalues that I already determined while I was solving for the natural response, I will take these vectors and use them to decouple the system, convert the system into multiple single degree freedom systems, solve for etas, and then go back to Q and that will be, this Q will be the forced response of the system. And we'll see a couple of examples on this. So the key here is that eigenvectors are orthogonal. That's what gives me the advantage of diagonalizing these matrices. The k divided by m are going to be the frequencies, which are basically the eigenvalues. So I do not really need to do all these calculations. Once I solve the natural response problem, I already have the frequencies here. So I know ahead of time, before doing all this, that I will have a system of decoupled equations, single degree freedom systems. The system will be, without looking at this derivation, I know that I will have an equation that looks like eta 1 double dot plus lambda 1, which is omega 1 squared, eta 1 equals, the only thing that I need to do is create this m tilde so that I can divide by m11 times f tilde. Of course, f tilde is P transpose times f. So it's a simple procedure. We'll see a couple of examples on this.